So we'll start our second module today, and in this lecture we'll see systems. So we completed our study of signals. Now we'll start our study of systems. Now what we are going to study here is how to model analytically the systems. So how to come up with equations which will represent systems. Now we already saw how to come up with equations that will represent different kinds of signals and how to analyze them and their properties. We'll do something very similar to systems. We'll analytically represent them using equations and then try to study their properties. Little flashback of what are systems. So we define systems as nothing but a black box which takes in an input and produces an output, right? And this input is a signal and the output is another signal, and we saw how to analyze these signals. Now we'll focus only on systems which have a single input and a single output. It is possible that there could be systems which take multiple inputs and produce multiple outputs. For example, if you take a system like a phone, it takes input from your video, from your camera, it takes input from your microphone, and then it also takes input from your battery, and then produces a signal which is like a radio frequency signal which connects to your base station, and then it also produces other signals like the variation in the light intensity in the display and so on. So in your mobile phone, there are multiple inputs and multiple outputs, but always we can focus on one particular input and one particular output. And that's what we'll see in this course, where we are going to restrict ourselves to a single input for a system and a single output for a system. So we'll see the system as a box which takes in a single input and then produces a processed output. Okay, so basically our system is nothing but a function f which will process or transform the input signal x of t into some other output signal. So if we know everything about this function f, then we say that we know completely about this system. So basically what we'll try to see is what are the properties of this function f which is transforming this input signal to some other output signal. So once we know these properties, we'll see how we can characterize this function f completely. So if we can completely characterize, so what do we mean by completely characterize? If I know a function completely, it means that given any input, I should be able to say what the output is. So if I say that I completely know a person, how do I say that I completely know a person? Then we say that if a particular person reacts in a certain way and you can predict that, okay, this person in this situation will react in this way, then you can say that I know that person completely. That's exactly what we are going to say here. If we can say that this system will produce this output for this input, then you completely know about this system. So how is it that we are going to completely know a system using mathematical models? That is what we'll see in this module. Okay, and what are the things that we need to know completely about the system? That are also the things that we'll see in this module. Okay. Okay, let us see some standard systems. So remember earlier we saw a simple example where you're trying to record an audio signal and there is an audio input and then you get the output here as an electrical signal. So the input here is an audio signal, output was an electrical signal, and that is a bigger system. And then we broke down that into smaller system where we had simply a capacitor whose input was a voltage signal which contained both DC and AC components, and the output was something which filtered out the DC components and gave only the AC components. So this is a small system, right, with single input and single output. So if you think about it, what exactly the system is doing is some kind of differentiation that we already saw, right? So the voltage if is fed to a capacitor, then the output current is nothing but the derivative of the voltage. So you can see what is the output here, which is basically some kind of derivative of the input. So in electronic circuits, the standard kind of systems that we would often end up encountering are those which are some form of combination of the integrator, differentiator, and the time shifter or the amplifier. Basically, these are all nothing but something like a combination of a capacitor or an integrator or a resistor or some kind of an operational amplifier or some kind of a delay circuit. Okay, so these are the very standard systems that we would often encounter. Of course, there are much more than these, but most often we can model many of these systems as combination of these four. So what is basically an integrator? So if you feed in an input x of t, the output is the integral of whatever is fed as the input. So let's say if function x of t is the input, then the output of this system would at every point be the area of the input till that point, right? That's what this integration means. So this means the area under x of t from minus infinity till t. So the output at the time t is the area under this curve till the point t. So if I try to find the value at this point, let's say this is t1, then it is the area under x of t from minus infinity till t1, right? So it will be this area. So this is the integrator. Now what is a differentiator? A differentiator is basically the slope of this input, at every time instant. So if you find what is the slope at this time instant, then you declare that to be the output. So then that is the differentiator. And the time shifter is basically whatever is the input, you shift in time that input. So if x of t was this, then the output is, let's say, shifted something like this. So this is a time shifted version or time delayed version. Okay. And of course, amplifier, if 1 volt is fed in as the input, then you get A volts as the output. This A can be 2, 5, it can be greater than 1 or it can be less than 1. So it can be anything. So these are the standard systems that we would often encounter in practice. And the nice thing about these systems is we completely know them already. This f function is already known, which means that we can fully characterize these systems. We know everything about their input-output relationship. Now, if there is something different other than these, then how do we characterize them? So that's the question that we want to answer. So in order to characterize these systems, first we need to understand certain properties of the systems. And what are the important properties that we need to know before we'll characterize a system? So basically these are properties that can help us to classify these systems. Once we understand the classifications, then we can say that, okay, these are class of systems which we can completely characterize and understand. That's what we'll try to do. So we'll study the properties first.